Today's topic is solution stoichiometry. Solution stoichiometry is found at the end of chapter 4 and brings together quite a few ideas that were previously discussed within the chapter. It begins with the question, what's in the beaker, as we consider chemical reactions that are taking place within water. The stoichiometry part, if we think back to chapter 3, when stoichiometry was first introduced, we have to be beginning with a balanced equation. The solution part, solution information includes concentration and volume. By combining concentration and volume, we can determine the number of moles. This question right here, when looking at any kind of stoichiometry, as we learned in chapter 3, mole amounts react with mole amounts. Therefore, when solution stoichiometry problems are involved, we have to be able to take concentration and volume to determine number of moles. How is this accomplished? So I see information given about a solution of hydrochloric acid. I see both the volume and the concentration, and we're asked how many moles of H plus are going to be in the solution. Hydrochloric acid is a strong acid. It's going to completely dissociate to give me H plus and chloride. If I have information involving the concentration and volume, I can use that to get to number of moles. So in this case, we have 125 mils of the solution. We need to convert those milliliters into liters, so we divide by 1,000. Now we have information in terms of the molarity. It's a 0.250 moles per liter of HCl. We know how many liters we have, so we combine those two in order to get to the number of moles of HCl. This skill right here of using concentration and volume to determine number of moles, really important at the end of chapter 4. Figure 4.16 gives us an overview involving solution stoichiometry problems. A lot of information here, but several of these are related back to things we've already been working on. Because there are stoichiometry problems, we need a balanced chemical equation, and we're going to be using the coefficients. Conversions between moles and mass, we've been practicing that quite a bit. We do that by using the molar mass. We look to the periodic table. If we're doing conversions between moles and molarity, if we look within our expression, moles per liter times liter to get to number of moles, we have 2 out of 3 terms. We have the number of moles, we have the volume in liters, and from that we can determine the unknown, which would be the molarity. Similarly, we could have 2 out of 3 where we know the number of moles and the molarity, and we're being asked to calculate then the volume. Let's apply some of these ideas. Sample exercise 4.14. The question, how many grams of calcium hydroxide are needed to neutralize 25 milliliters of a 0.1 molar nitric acid solution? I see a stoichiometry problem, so I have to start with a balanced equation. This is an acid-base neutralization reaction. Calcium hydroxide is the base, nitric acid's the corresponding acid. It produces water, and the resulting salt, calcium nitrate. We're interested in how one reactant is combining with the other ones. The product, not really important for us. It's helpful to see so that we properly write the balanced equation, but we're really just interested in determining how many grams of one of the reactants we need to neutralize the other. We know all the information about one of the reactants, the nitric acid. I see solution information involving the volume and the concentration. So let's combine that to get to number of moles. It's 25 milliliters of solution, so if we divide by 1,000, we can determine how many liters of the solution we have. Now, if we take moles per liter times number of liters, that tells me how many moles we have of the nitric acid. So we have 0.0025 moles of nitric acid. Based on the balanced equation, we would need half that amount of base. I say half that amount because look at the coefficients. For every 1 calcium hydroxide, it requires 2 moles of nitric acid. So now we know how many moles of the base that we need. It's being asked how many grams that is. So let's just look to the molar mass. So if we look to the periodic table, calcium hydroxide is just over 74 grams per mole. We know how many moles of it we need, so this would be used to calculate how many grams of the calcium hydroxide. Key features that I see here: balanced equation, and we knew everything about one of the reactants. We had solution information, so we knew everything about the nitric acid. Oftentimes, solution stoichiometry problems are set up as scenarios, and those scenarios might include titrations. Titrations, that's an important topic, and you're going to use that quite a bit in Chemistry 1220. A scenario is listed here on the left-hand side. The first thing I want to extract from the scenario, I need a balanced equation. So this is another acid-base neutralization reaction, this time involving sulfuric acid and sodium hydroxide. So we want to begin by writing a balanced equation. Solution information is given, so we're going to go back to the expression moles per liter times number of liters gets me number of moles. For the sulfuric acid, we know everything about it. We know the concentration and the volume. By combining the concentration and the volume, we can determine number of moles. So we know everything about one of the reactants. We know how many moles were involved in the reaction. We can now use the balanced equation and figure out how many moles of the other reactant are involved. I see a 2-to-1 ratio because for every 1 sulfuric acid, it requires 2 moles of sodium hydroxide. Now we know everything about the sodium hydroxide in terms of the number of moles that were involved and the volume that was involved in the reaction as well. I might have misspoke. I guess we don't know everything about it. We know 2 out of 3 terms. We know the number of moles that were involved, we know the volume, and given 2 out of 3, we're solving for the last one, the molarity. If we do that, we find that the resulting base solution would be 2.28 molar sodium hydroxide. One more example for you. We find that the solution stoichiometry problems are going to bring together ideas previous in the chapter. Those could be acid-base neutralization reactions. They could also be precipitation reactions. And when I'm thinking precipitation, I'm thinking solubility guidelines that we saw earlier in the chapter. So we're going to be combining a calcium 2 nitrate solution. A precipitate forms when it reacts with sodium hydroxide. What would be the precipitate? And then do a calculation. How many grams of sodium hydroxide would be required to form the maximum amount of the precipitate? So cadmium 2 nitrate is reacting with sodium hydroxide. By looking to the provided information, I think that we're going to form cadmium hydroxide. Hydroxides are insoluble. There's a few exceptions, but the cadmium is not an exception. So the cadmium hydroxide is going to be the resulting precipitate. Sodium nitrate, those remain as spectator ions. So it looks like we have all the information we need for one of the reactants, the cadmium nitrate. Coming back to the solution information, if we know concentration and volume, we can get to number of moles. And in this case, for the cadmium nitrate, we do have concentration and volume, so we can get to the number of moles. If we then look at the balanced equation, there are 2 sodium hydroxides for every 1 cadmium nitrate. So the number of moles that we need for the sodium hydroxide is double. And in this case, it's asking it for the sodium hydroxide in grams. So if we know how many moles of sodium hydroxide are required, we can look to the periodic table, get the molar mass for the sodium hydroxide, and figure out how many grams are involved. In today's class, we're going to practice solution stoichiometry problems. We have a few easier problems to sort of see how the different relationships fit together. Then we have several moderate problems to try. The moderate level problems, those are most representative of what you'd find on an exam for this topic. And then there's one that is the most difficult. It's a real challenge problem. As time allows, let's try that and see if we can see how the different ideas fit together in that particular scenario.